Welcome back. Problem 9-26. This problem is taken from chapter number 9, Stress Transformation, and the book name is Mechanics of Material by R.C. Hibbler. So, statement is the bracket is subjected to a force of 3 kips. Determine the principal stress and maximum in plane shear stress at point A on the cross section at section AA. Specify the orientation of this state of stress and show the result on the element. So you can see this is the bracket that is subjected to 3 kips load, tensile load. This cross section at section A is shown over here. You can see this is the breadth, this is the height, and this is the web flange, and this is the web. This is web and this is flange. All the dimensions are mentioned. So you have to find the principal stresses and maximum in plane shear stress at point A, and you have to specify the orientation and state of stress. So let's start with the solution. So when you section it at section AA, so here I have shown, so you will be having a reaction, a normal force that is perpendicular to this surface, and this will be equal to N. Clear? You will be having a shear force as well as you will be having a movement that will be in this direction. Clear? So you will find this V, M and N by using equation of equilibrium. The first equation of equilibrium, that is sum of all forces along y direction must be equal to 0, and upward force is taken as positive. Okay, so you can see only V is acting downward, so minus V is equal to 0. It means that this shear force is equal to 0. Now we'll find this N by using equation of equilibrium, that sum of all forces along x direction must be equal to 0, and force in this direction is taken as positive. So you can see N is in positive direction and this 3 is in negative direction. Their sum must be equal to 0. So from here we will get this N is equal to 3 kip. Now we'll find this moment, and the equation will be sum of all moment about section AA must be equal to 0, and taking the counterclockwise movement as positive. So here you can see this distance from top till this top surface is 3 inch. So this is 3 inch, and this half portion which you can see here, this is 2 inch, so half will be equal to 1. So total distance will be 4 inch. So distance from this till the mid of this is 4 inch. Clear? So you can see a movement about section AA. So this force into perpendicular distance is this one, 4. Clear? And this is producing counterclockwise movement, so it will be positive. The second movement about this section AA is this movement which is clockwise, and that will be negative, but their sum must be equal to 0. So I will write 3 multiplied by 4 minus M is equal to 0. So from here M will be equal to 12 kip into inch. Okay, kip into inch. Now we have all these 3 unknowns. So you can see here that here we, for normal stress, I will write normal stress. For finding normal stress, sigma, that is the combination of this normal load over this face, that will be equal to N divided by A. Clear? And due to this movement in this direction and due to this movement, it will be in bending stress. So due to bending stress, this will bend like this. The upper portion is in tension while lower is in compression. Clear? So it will be positive plus M into Y divided by I. So this N by A is stress due to normal force. Clear? This is the stress, and this stress is due to the stress due to bending moment. Clear? Okay. Now we'll find this A and I, which are the section properties. So section properties, A is the area of this cross section. So you can see this is the cross section. So if I take it like this is the whole area 1/2 inch, and then subtract these 2 portions. So we will get the area. So area is equal to 2 multiplied by 1 minus, you can see that this height is 2 minus 0.5 minus 0.5, which is 1.5, and this remaining two portions is 1 minus 0.25, which is 0.75. So I will write 0.75 multiply by height, which is 1.5, and when you calculate it you will get this area comes out to be 0.875 square inch. Now we'll find I, which is the second moment of inertia about this neutral axis, and since this is symmetrical about the center, so we will take moment of inertia I, which is equal to 1 over 12, its breadth, which is 1, and height is 12. So 1 into not 12, 2, 2 cube. So this will be the moment of inertia when you take this as a rectangular. And now we will subtract the moment of inertia of the remaining these two portions. So I will write minus 1 over 12. The remaining breadth is 0.75, which you have seen over here, and height is 1.5 cube. So when you calculate it, you will get 0.45573 inch power 4. Now you have all these values, and you can see that we have to find the principal stress at point A. So A is at a distance of 1 from this neutral axis. So Y is equal to 1 inch. So I will write Y is equal to 1 inch for point A. Now you have all the values, you can just put it. N is 3 kips, so 3 divided by area is 0.875 plus moment is 12 kips, so 12 into Y is 1 divided by I is 0.45573. So when you solve this, you will get the stress at point A, which comes out to be 29.76 KSI. So this is the normal stress that is acting at point A. Now for shear stress, we know that shear stress is equal to V into Q, V into QA divided by I into T. So QA will find QA. So QA is equal to Y dash bar into area. Since this is point A, so above this point A there is no area. Area is equal to 0. So it means that QA will be equal to 0. So here then this shear stress will be also 0. Now we will draw the state of stress at point A can be represented as, if I draw the element and show the state of stress, so only we have sigma A normal stress in horizontal direction, and that is like this, which is sigma A is equal to 29.76 KSI, and that is also equal to sigma X. There is no stress in Y direction, so it will be 0, and there is no shear stress, so state of stress at point A, Now we'll find the principal stresses. So for principal stresses, I will write principal stresses. So here we have sigma X is 29.76 KSI, sigma Y is equal to 0, and tau of XY is also 0. So principal stress, you can see that this is sigma 1 comma 2 is equal to sigma X plus sigma Y divided by 2 plus minus sigma X minus sigma Y divided by 2 whole square plus tau of XY whole square. Okay, so when you put the value sigma 1 comma 2 is 29.76 plus 0 divided by 2 plus minus 29.76 minus 0 divided by 2 whole square plus 0 square. So So when you solve this, you will get sigma 1 comma 2 will be equal to 29.76 divided by 2 plus minus 29.76 divided by 2. So from here, if you take plus, sigma 1 will be equal to 29.76 divided by 2 plus 29.76 divided by 2, which is equal to 29.76, and the unit will be KSI. And sigma 2 will be equal to 29.76 divided by 2 minus 29.76 divided by 2, which is equal to 0 KSI. So we will get sigma 1 is 29 point, I will round off it. So this, and sigma 2 is equal to 0 KSI. Now you can also find this sigma 1 and sigma 2 by using Mohr circle. So we will also explain that this is a horizontal axis and this is the vertical axis. On horizontal axis we will take normal stress, on vertical axis we will take the shear stress. So for that we will need the pair sigma x comma tau of xy and sigma y comma tau of minus tau of xy. So 29.76, or you can also say that this is 29.8 comma 0 and 0 comma 0. So if you plot first point 29.08, let one division 1, 2, 3, 4, 5 is of 5 KSI. So 5 and this is 30. So 29.8 is approximately 30. So this point will be 29.8 comma 0. And this point will be equal to 0 comma 0. And when you draw a circle which are passing through these 2 points, clear, you have to draw it perfectly. So you will get it like this. Here you can see that this point is sigma 1 and here this is sigma 2. So sigma 2 is 0 and sigma 1 is 29.8 KSI. Now I will represent this principal stress on the state of element R. So this is sigma 1, which is equal to 29.8 KSI, and there is no sigma 2, so it is the only state of stress sigma 1. For in plane shear stress, we have formula maximum in plane shear stress. We have formula tau max in plane is equal to sigma x minus sigma y divided by 2 whole square plus tau of xy square. So put the value, you will get 29.7, 29.8 minus 0 divided by 2 whole square plus 0 whole square under the root. And when you calculate, it will be 14.9 KSI. Okay. Again, you can see that the center of this circle will be equal to sigma average comma 0. This is the center, and sigma average is sigma x plus sigma y divided by 2. So when you calculate it, 29.8 divided by 2 will be again 14.9. Clear? So this point is 14.9 comma 0. Okay, and this is the maximum in plane shearing stress. Here you have sigma, at this point you have sigma average comma tau in plane maximum, and you can see this tau in plane maximum in plane is equal to radius of this circle, and radius of this circle is again can be computed by this formula, which is equal to this. Let me write it: sigma x minus sigma y divided by 2 whole square plus tau of xy square under the root, and you will get the same 14.9 KSI if you use the Mohr circle. Okay, Now we will find the orientation of maximum in plane. So for that we have tangent of 2 theta s is equal to minus sigma x minus sigma y divided by 2, clear, divide by tau of x y. So if you put the value minus 29.76 minus 0 divided by 2 divided by 0 will give you infinity. So it means that 2 theta s is equal to tangent inverse infinity. So 2 theta s is equal to 90 degree, and if you want to find theta s, so theta s is equal to 45 degree or minus 45 degree. Clear? Now we'll move to our next page. So we have theta s is equal to 45 and minus 45. So you can, theta s is 45 degree or theta s is equal to minus 45 degree. So put this theta is equal to minus 45 degree in tau of x dash y dash, which is the transform stress when the element is rotated through any angle. So sigma x minus sigma y divided by 2 into sine of 2 theta plus tau of xy cos of 2 theta. So minus 29.8 minus 0 divided by 2 into sine of 90 degree minus 90 because theta is minus 45 plus 0 into cos of minus 90 degree. So when you calculate it, you will get tau of x dash y dash is equal to 14.9 ksi. So this is the positive value, which is maximum in plane shear that occurs at 45 degree shear stress. Now average shearing stress comes out to be sigma x plus sigma y divided by 2. So 29.8 plus 0 divided by 2 will give you 14.9 ksi, and we will represent it on state of element. So let this is your initial x, this is your y, and now angle is minus 45 clockwise. So let this is minus 45 degree clockwise, and this new transform y axis will be y dash will be this. And if you draw the element like this, so this will be the element, clear, and you can see that average shearing stress will be like, it will be like perpendicular to this surface, perpendicular to this surface, perpendicular to this surface, perpendicular to this, and this is sigma average, all are sigma average, and tau of xy is positive, so it will be like our maximum in plane shear stress will be like this one. This is tau in plane maximum. So that was all about this problem 9-26, in which we have calculated the principal stresses, clear, which is sigma 1 comma sigma 2, and we represented it on element and specify the location. Then we discussed the maximum in plane shear stress using normal equation as well as by using Mohr circle, and then we calculated the average normal stress at this angle theta is 45, and specified the state of stress at this theta s, which is minus 45. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 9-27. This problem is exactly the same like problem 9-26 that is taken from chapter number 9, stress transformation and mechanics of material by R.C. Hibbler is the book name. Statement is the bracket is subjected to the force of 3 kips. Determine the principal stress and maximum in plane shear stress at point B on the cross section at section AA. Specify the orientation of state of stress and show the result on the element. So you can see this is a bracket and this is a 3 kips axial or tensile load is applied. The at section AA, the cross section of this is shown, that is I beam, and you have to find the principal stresses at point B and maximum in plane shear stress, and you have to specify the state of stress and show the result on the element. So in problem 9-26 we solved this. This is exactly the same, but instead of point A, here we will solve it for point B. So let's start with the solution. So first step is that if we section it at section AA and draw the free body diagram, so here at this section we will be having a reaction force which is normal force N, and you will be having a shear force V, clear, and you will be having a moment M. So we'll find this V, M, and N by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along y direction must be equal to 0 and force upward is taken as positive. So only V which is acting downward is negative and there is no other force. So it means that shear force acting will be equal to 0. Now we'll find this and by using equation of equilibrium that sum of all forces along x direction must be equal to 0 and force in this direction is taken as positive. So 3 is in opposite direction, so minus 3 plus this n which is in positive direction is equal to 0. So from here we will have n is equal to 3 kip. Now we'll find this moment about section AA. So for that I will apply the equation that sum of all moment about section AA must be equal to 0 and movement in counterclockwise is taken as positive. So here you can see that this is 3. So till the mid of this section, this total distance will be 4 inch. How? Let me show you. This is 4 inch. So this is 3 and this is the cross section. So half of this will be equal to 1 inch. Clear? 1 inch. And 3 plus 1 is equal to 4. So I will write it, this distance is 4 inch. So you can see that this force 3 into perpendicular distance about section AA is 4 and this is producing clockwise, so it will be negative. So I will write it minus 3 multiplied by 4, and this external reaction moment which is clockwise, counterclockwise, this is counter 3 into 4 is producing, this is the force and this is counterclockwise, so it will be positive. So this will be positive and the other one will be negative. So kindly correct it in problem 9-26. Again you will get the same value. Moment will be equal to 12 kips into inch. Now you have this, all these things. So you can see for normal stress, which is equal to sigma, that is the combination of this normal stress that is acting on this surface and due to this movement and due to this movement it will produce the bending stress. So this portion will be upward will be in tensile and downward will be in compression. Since we are dealing with point B, clear, so this portion will be in compression, it will be taken as negative. So I will write it N by A is the normal stress minus M into Y divided by I. Clear? Now we will find A and I are section properties. So we will find first that section properties. So cross-sectional area of this can be obtained if we take it as a rectangular box which is 1 by 2 inch and then subtract these two portions. and this 2 portion, this height is 1.5, because 2 minus 0.5 minus 0.5 is 1.5, and this remaining 2 portion is 1 minus 0.5 is 0.75. So I will write it 2 multiplied by 1 minus 0.75 multiplied by 1.5, that will give you 0.875 square inch. And I for this beam is equal to, if I take it as a rectangular box and find the moment of inertia about this axis, so this will be breadth and this will be height. So 1 over 12, B is 1 and H is 2 cube, and then minus these two portion, minus these two portion, and minus 1 over 12, breadth is 0.75, because 1 minus 0.2 will be 0.75, and height is 1.5 cube. And when you solve this, you will get I will be equal to 0.4573 inch power 4. And what about y? So y is distance from neutral axis till the point B, and that is 1. Clear? This is 1 inch. So y is 1 inch. We haven't take minus y because we already assume that below is the compression. So this is normal stress. So normal stress is N is 3 divided by area 0.875 minus M is 12 into 1. Y is 1 divided by I is 0.45573. And when you solve it, you will get stress at point B will be equal to minus 22.90 KSI. Okay, so this is the normal stress. Clear? And what about shear stress? So we know that shearing stress at point B is equal to V into QB divided by I into T. So this is point B. Clear? So about point B there is no area. So we know that QB is equal to Y dash bar into A. So area A is equal to 0 because there is no area above A. So QB is equal to 0. So it means that shearing stress at point B will be equal to 0. Now if we draw the state of stress element, so it will be like this. If this is the element, clear? This is the element. So only stress in x direction is compressive stress, that is minus sigma b, or sigma x is equal to sigma b is equal to minus 22.90 ksi. Clear? So there is no stress in y direction and there is no shear force, so it will be like this. So here you can see sigma x is equal to minus 22.90 ksi, sigma y is equal to 0, and tau of xy is again equal to 0. So for principal stresses, you can calculate these stresses by using Mohr circle or using this formula sigma 1 comma 2 is equal to sigma x plus sigma y divided by 2 plus minus under the root sigma x minus sigma y divided by 2 whole square plus tau of xy whole square. I have solved problem 12.9-26 by using both method. Here I am going to solve it by using this formula. So put the value sigma x is minus 22.90 plus 0 divided by 2 plus minus under the root minus 22.90 divided by 2 minus 0 whole square plus 0 square under the root. So when you solve this, you will get sigma 1 will be equal to minus 22.90 divided by 2 plus 22.902 divided by 2, which is equal to 0. And you will get sigma 2 will be equal to minus 22.90 KSI. So these are the principal stresses. So if you want to represent on the element so representation will be sigma 1 is 0, so it will be like this, sigma 1 is equal to 0, and your sigma 2 will be compressive. that is minus 22.90, and this will be minus sigma 2, which is 22.90. Now we will find the maximum in plane shear stress. Maximum in plane shear stress, which is equal to tau max in plane, and that is equal to sigma x minus sigma y divided by 2 whole square plus tau of xy whole square under the root. So just put the value minus 22.90 divided by 2 minus 0 whole square plus 0 square under the root. So you will get maximum in plane shearing stress comes out to be 11.5 KSI, and we will have average shear stress that will be equal to sigma x plus sigma y divided by 2, and that will be minus 22.90 plus 0 divided by 2 is average normal stress. And that when you calculate it, it will be equal to minus 11.5 KSI. Now we are going to find out the orientation of maximum in plane shear. So for that we have formula tangent of 2 theta s is equal to minus sigma x minus sigma y divided by 2 whole square divided by tau of xy. So minus 22.590 minus 0 divided by 2 whole square. This is not square, okay, remove this, okay, divide by tau of xy, which is 0. So it means tangent of 2 theta s is equal to infinity. So from here t2 theta s is equal to tangent inverse infinity, and we will get theta s will be equal to 2 theta s will be equal to 90 degrees. So theta s is equal to 45 degree or minus 45 degree. So how you will know that what will be the direction of theta s? So put theta s is equal to 45 degree in equation, which is transform equation for shear stress, is equal to minus sigma x minus sigma y divided by 2 into sine of 2 theta plus tau of xy cos of 2 theta. So when you put the value of sigma x, which is equal to minus 22.90, and 2 theta is 2 theta is 90 degrees, so you will get it 11.5 KSI, which is positive. Now if you want to represent it on a state of stress element, so let this is initial x is x, this was y, clear, and when you rotate it 45 degree counterclockwise, because theta s is positive 45 degree counterclockwise, clear. So your new y dash will be like this, and if you draw the element like this, clear. So your average shear stress, which is sigma average, is equal to this value, where is 11.5, this all this will be sigma average, clear, and your tau of x dash y dash will be 11.5, and this will be in y dash positive direction. I will choose another color. This will be like this. This will be tau of x dash y dash, or maximum in plane shearing stress. This is tau of in plane maximum, or tau of x dash y dash. And this is the representation of state of stress element, and specify the location. And that was all about this problem 9-27. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest video. Also share my videos with your friends so that they may also learn and help me in growing my channel. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 9-28. In this problem is taken from chapter number 9, that is stress transformation, and the book name is Mechanics of Material by R.C. Hibbler. So statement is the 25 millimeter thick rectangular bar is subjected to axial load of 10 kilonewton if the bar is joined by weld which makes an angle of 60 degree with the horizontal. Determine the shear stress parallel to the weld and normal stress perpendicular to the weld. So you can see this is a rectangular bar having height is 80 millimeter and the thickness is 25 millimeter, and this bar is subjected to 10 kilonewton axial load, and this bar is made by joint it using weld which makes an angle of 60 degree from the horizontal. So you have to find the shear stress along this weld and the normal stress that is perpendicular to this weld. So let's start with the solution. So first step is that you can see you have a 10 kilonewton load, 10 axial load. So we'll find the axial stress, and that axial stress is equal to force per unit area. Clear? So force is 10 kilonewton, so 10 into 10 raised to power 3 newton, and area over which it act is 80 multiplied by 25 millimeter. So we will convert this millimeter into meter. So length thickness, which is 0.025 meter, multiplied by the height, which is 0.08, and the unit will be square meter. So when you solve this, you will get it 5 into 10 raised to power 6 Newton per meter square, and we will get 5 into 10 raised to power 6 Pascal, and when you convert it into megapascal, so it will be 5 megapascal. Now you can see that we have only normal stress in x direction is 5 megapascal. So this is x direction and this is your y direction. Clear? There is no other load applied. So what we will get is that if you draw the state of stress on element, so this you will be your sigma x. Clear? In this direction, this is sigma x, which is equal to 5 megapascal. So in this case you have sigma x is 5 megapascal. You do not have sigma y, that is 0, and there is no shear stress, so tau of xy is also equal to 0. Now here you can see that we have been given that this weld which makes 60 degree, so you can either take theta as 60 degree counterclockwise, which will be positive, or if you can see that let this is your x-axis and this is your y-axis. So if you take this remaining, which is 30 degree in clockwise direction, r theta is equal to minus 30 degree. Minus 30 degree means 30 degree clockwise. Clear? So we will take here theta is equal to minus 30 degree, and after that we will find the transform stress that will be acting on this shear stress on this surface along parallel to the weld and the normal stress perpendicular to the plane. So we know that transform stress sigma x dash is equal to sigma x plus sigma y divided by 2 plus sigma x minus sigma y divided by 2 into cos of 2 theta plus tau of xy sine of 2 theta. Now you have all the values, just put it. So 5 plus 0 divided by 2 plus 5 minus 0 divided by 2 into cos of theta is minus 30. So cos of 2 theta is minus 60 degree plus 0 into sine of minus 60 degree. That will give you transform stress in x direction, in new x dash direction. Clear? And that when you calculate it, you will get sigma x dash comes out to be 3.75 megapascal. Now we'll find the shear stress that will be parallel to the weld, and that shear stress of x dash y dash will be equal to sigma x minus sigma y divided by 2 into sine of 2 theta plus tau of xy into cos of 2 theta. So put the value 5 minus 0 divided by 2 into sine of minus 60 degree plus tau of xy, which is again 0, into cos of minus 60 degree. And when you calculate it, you will get the transform stress, shear stress comes out to be 2.17 megapascal. So this is the stress, transform shear stress, and this is the transform normal stress that will act on the element. So if you draw the element initially, this is your x-axis, here this is your y-axis, and you have seen that we have transformed y-axis. This is 30 degree minus 30 degree, that is clockwise. Clear? So here this x dash will also move to, this is x dash, this is your new axis y dash, and this is again 30 degree, that is clockwise. Clear? And when we draw the element, so element will be like this. Clear? And we will be having the normal stress in this direction, which is in x dash direction, that is positive. So it will be like this, sigma x dash will be like this, and your top x dash y dash will be like this. So tau of x dash y dash is 2.17 megapascal, and sigma x dash is 3.7 megapascal. Also, if you want to draw it on this element, so you can see this stress, shear stress, is parallel to this surface, clear, in to the weld, and this stress which is normal to this surface, that is sigma x dash. And that was all about this problem 9-28. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 9-29. This problem is taken from chapter number 9, that is stress transformation, and book name is Mechanics of Material by R.C. Hibbler. So statement is the 3-inch diameter shaft is supported by smooth bearing, thrust bearing at A and smooth journal bearing at B. Determine the principal stresses and maximum in plane shear stress at a point on the outer surface of the shaft at section AA. So you can see this is the shaft. At point A we have smooth thrust bearing, and at point B we have journal bearing. The loading here is shown, this is axial load, and there are two torques at two different points opposite to each other are shown over here. So you have to determine the maximum principal stresses and in plane shear stress at this section AA on the outer surface of this shaft. So let's start with the solution. So first step is that if you remove this smooth thrust bearing, so you will be having a reaction, vertical reaction force, which is equal to RAY, and as well as there will be a horizontal reaction force which will be equal to RAX. And similarly, if you remove this journal bearing, smooth journal bearing, so you will be having only vertical reaction force, that is RB We will find this unknown reaction force by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So here we can see that this is your x-axis. On vertical you have y-axis, and in this direction you have z-axis. Clear? So remove this. Remember this sum of all forces along y direction must be equal to 0. So RAY, which is upward, plus RB is equal to 0. So this is your equation number 1. Now we'll apply another equation of equilibrium, that sum of all forces along horizontal direction must be equal to 0 and force in this direction is taken as positive. So horizontally we have 3 kips and RAX. So RAX minus RAX, because that is opposite to this x, plus 3 kips is equal to 0. So it means that RAX is equal to 3 kips. Now we will find this RB by using equation of equilibrium, that sum of all moments about point A is equal to 0, taking the counterclockwise moment as positive. So about this point A, one moment will be RB into perpendicular distance. The total distance is this one, which is not given. Let this distance is equal to L. So I will write it RB into length L, and this is producing counterclockwise rotation, so it will be positive. Clear? So and we have torques about this point. This is point A, our x-axis. So one is 500 counterclockwise, another one is clockwise. So minus 500 plus 500 will be equal to 0. So it means that RB into length is equal to 0. So from here length cannot be 0. So it means that RB is equal to 0. Now you have RB is equal to 0. So put RB in equation number 1. So you will get RAY is also equal to 0. Now you have these forces. It means that these bearings are not offering any vertical reaction. So what we will do is that now you will cut this shaft at section AA, here at section AA, and you will draw the free body diagram. So let me draw it. Let this is the shaft. Clear? At this end we have 3 kips load. Clear? That is 3 kip. This is your point B. Clear? And there is a torque of 500 in clockwise, 500 pounds into feet, and this is your section AA. At this point we have x-axis in this direction. Clear? Similarly y in vertical direction, and z is in this direction. This is your axis. So when you cut it, so you will be having a normal force that will be acting opposite to this will be normal force. Let this force is N, and you will be having a torque opposite to this, that will be counterclockwise, and this torque will be represented as T. So we'll find this torque and N by using equation of equilibrium, that sum of all forces along x direction must be equal to 0 and force in positive x direction is taken as positive. So you can see this is opposite to this x, so it will be minus N, and this plus 3 is equal to 0. So it means that N is equal to 3K. Now we'll find this torque. So you can see that this is counterclockwise torque and this is clockwise torque. So their sum of all this torque must be equal to 0. So T will be equal T minus 500 is equal to 0. So it means that this torque is equal to 500 pounds into feet. That will be in counterclockwise direction, this reaction torque. Now we will have, due to this normal force, you can see this normal force, we will be having normal stress, and due to this torque we will be having a shear force acting on it. So first we will find the normal stress. So normal stress will be equal to force per unit area. So N is given as 3 kips. So 3, that is compressive load. You can see that this is compressive, this and this is compressive, causing the shaft to compress. So it will be minus, I will write minus, no, minus 3 kips. So 10 raised to power 3, it will be converted into pounds. And what about area? So this is circular shaft having diameter 3 inch. So it will be, area will be equal to pi by 4 d square, pi by 4 d square, and d square is 3. Clear? That will give us minus 3000 divided by area will be 2.25 pi. This will be pound and this will be inch square. So that this stress will give you minus 4 to 4.41 pound per square inch. So that will be equal to psi. Now we'll find the shear stress due to torque. Shear stress due to torque T. We know that shear stress due to torque T is equal to T into C divided by J, where T is torque, C is the radius, and J is polar moment of inertia. So J for circular rod having, if D is equal to 3 inch, so radius will be equal to 3 divided by 2 is equal to 1.5 inch. So J for rod having radius R is given as pi by 2 r power 4. Clear? So pi divided by 2 into r is 1.5 power 4. So when you calculate it, you will get 2.53125 inch power 4. And C is distance, C is radius, distance from neutral axis till the topmost. So that is radius, and that is 1.5 inch. So now you just put the value, so you will get the shear stress is equal to torque, which is equal to 500 pounds into feet. So we will convert it into inch. So 1 feet is 12 inch. So this will be, torque will be equal to pound into inch, and C will be 1.5 divided by J. This will be inch divided by J is 2.53125 pi. Clear? There is a pi as well over here. Okay. And this unit will be inch power 4. So when you calculate it, you will get the shear stress comes out to be 1131.77 psi. So if you draw the state of stress on the element like this, so you can see that you have stress in x direction is minus 4 to 1, 4 to 4, that is compressive. So your sigma x will be equal to minus 4 to 4.41 psi. There is no stress in y direction, and we have shear stress tau of xy. So this is y direction, this is tau of xy. That will be like this. This is tau of xy. Tau of xy, that is 1131.77 psi. Now we are going to find out principal stresses. So we have sigma x is minus 4 to 4.41 psi. you have sigma y is equal to 0 and tau of xy is 1131.77 psi. So first we will find principal stresses. So principal stress is equal to sigma 1 comma sigma 2 is equal to sigma x plus sigma y divided by 2 plus minus under the root sigma x minus sigma y divided by 2 whole square plus tau of xy square. So put the value minus 424.41 plus 0 divided by 2 plus minus 4 minus 4 to 4.41 minus 0 divided by 2 whole square plus 1131.77 square, and this will give you sigma 1 comma 2. So when you solve it for plus, take this value plus this will give you sigma 1, and when you solve this due to limitation of space you can solve it. Sigma 1 is 939.28 psi, and when you take this term minus this term, so you will get sigma 2, and this sigma 2 comes out to be minus 1363.70 psi. So these are the principal stresses. Now we'll find the maximum in plane shear stress. So that is maximum in plane, and for that we have formula that is equal to sigma x minus sigma y divided by 2 whole square plus tau of xy square. So minus 424.41 minus 0 divided by 2 whole square plus 1131.77 square under the root will be equal to the in plane maximum shear stress, and that comes out to be 1151.49 psi. Or you can say that maximum in plane shear stress in term of KSI will be equal to 1.15 KSI. So this is the value of maximum in plane shear stress, and these are the principal stresses that occur on the outer surface of this shaft at section AA. And that was all about this problem 9-29. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Also share it with your communities so that they may also learn and help me in growing my channel further. Welcome back. Problem 9-31. This problem is taken from chapter number 9, that is stress transformation, and book name is Mechanics of Material by R.C. Hibbler. So statement is determine the principal stress at point A on the cross section of the arm at section AA. Specify the orientation of this stress and indicate the result on the element. So you can see this is the arm that is having a pin support at point B, and there is a rope which gives support to this arm, and there is a load of 500 Newton is applied. So you have the cross section at section A is shown over here, that is I beam. So you have to find the principal stresses at point A and then specify the orientation and indicate the result on the element. So let's start with the solution. So first step is that we will determine the support reaction. So I will write it support reaction on arm, reactions on arm. So what we will go do is that you can see this is the arm, and if you remove this support, pin support at point B, so you will be having horizontal reaction force which is Bx, and there will be a vertical reaction force which will be represented as Py. And if you can see that this is the rope CD which exert a force of FCD on this arm, and that makes this angle is 30 degree, because this is 60, this is 90, and this will be 30 degree. So we'll apply equation of equilibrium. That first equation of equilibrium is that sum of all moments about point B is equal to 0, and taking the counterclockwise moment as positive. So you can see this is the point B. These two forces are not producing moment because they are passing through it. So we have only two forces, FCD and 500. One is known and other is unknown. So you can find FCD. Okay, so this FCD will have two component. One is along x-axis, which is FCD x component, and other one is this y component, which is FCD y component, and this FCD y component will be equal to FCD into sine of 30 degree. Clear? And FCD x will be equal to FCD cos of 30 degree. So you can see this FCDX is passing through this point, so it is not producing movement. So only the force which is producing movement is this FCDY, and the perpendicular distance is this one, which is 0.3, and this is producing counterclockwise movement, so it will be positive. So I will write it FCD into sine of 30 degree multiplied by perpendicular distance is 0.3. The second moment that is produced due to this 500 Newton load and perpendicular distance is this one, which is equal to 0.65. This is 0.3 and this is 0.35. So it is 0.65, and it is producing clockwise movement, so it will be negative. So I will write it minus 500 into 0.65 is equal to 0. So when you calculate it, you will get FCD will be equal to 500 into 0.65 divided by sine of 30 degree multiplied by 0.3, and that will give you 2166.67 Newton. So this is FCD. Clear? Now we'll find this Bx and By by using equation of equilibrium, that sum of all forces along x direction must be equal to 0, and force in this direction is taken as positive. So Bx, which is acting in positive direction, and the other force along horizontal is this FCDx, will be equal to, their sum must be equal to 0. So I will write Bx minus FCD x component is equal to 0. So from here, Bx is equal, Bx minus FCDx is FCD cos of 30 degree is equal to 0. So Bx will be equal to FCD cos of 30 degrees. So you have the value of FCD, which is 2166.67 into cos of 30 degree. That will give you Bx. So Bx will be equal to 1876.39 Newton. Now we'll find By by using equation of equilibrium, that sum of all forces along y direction must be equal to 0, and upward force is taken as positive. So you can see one force is upward is this one, the second one is this one, and third one is downward. Their sum must be equal to 0. So upward force is taken as positive. So By clear, minus 500, which is downward, plus FCD y component, which is equal to FCD is 2166.67 into sine of 30 degree is equal to 0. So when you calculate it, you will get By is equal to minus 583.33 Newton. So this value is negative. It means that our assumed direction is wrong. It should be downward. So By should be downward. So I will write assume direction of by is wrong and it should be downward. Okay, now we have all these reaction forces. So what we will do is that you will cut this beam or arm at section AA and draw the free body diagram of this portion. Clear? So let me draw it. I will write internal loading. We are going to find internal loading at section AA in order to show what are the forces acting over here. So when you section it at this point, so this is section AA and this will be the beam like this, not like this. It will be like this. So this is point BX. So BXB, this is point B. So we have BX in this direction, clear, and BY is in downward direction because we have find out that it should be in downward direction BY. And the distance from this point B and section AA is 0.15. You can see over here this distance is 0.15, and when you section it, so you will be having a normal force at this point, and this normal force should be opposite to this bx, and you will be having a shear force that will be acting upward, and there will be a movement which will be in clockwise direction. So we'll find this V, M, and N by using equation of equilibrium. So what are these equations? So first equation is that sum of all forces along x direction must be equal to 0 and force in this direction is taken as positive. So Bx is in positive while N is in negative. So Bx minus N is equal to 0. So it means that N is equal to Bx, and Bx is 1876 1876.39 Newton. Now we will find this V shear force, and for that we will apply sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So V is upward, so V minus By is equal to 0, and from here we will get V is equal to By, and this By is 583.33 Newton. And we will find this M by using equation of equilibrium, that sum of all forces about this point, that this is point O, about point O is equal to 0, or section AA is equal to 0, and taking the counterclockwise movement as positive. So you can see these two forces are not producing movement and this one, because it is passing through point O, so only movement is producing is this By about point O, and perpendicular distance is 0.5. This is producing counterclockwise, so it will be positive, and this external movement which is M, that is negative. Their sum must be equal to 0. So I will write it 583.3, which is By, into perpendicular distance is 0.15 minus this M is equal to 0. And from here you will get this moment will be equal to 87.5 Newton into meter. Okay, now you can see that you have this normal force, you have this shear force, and you have movement. So due to this normal force, you will be having a normal stress. Due to this shear force, we will have a shear stress. And due to this movement, and due to this, it will be bent like this. Okay, it will be bent like this. Clear? So here we will have normal stresses and shear stress. So let me write it: normal stress and shear stress. So normal stress, which is represented as sigma, will be the combination of this normal stress due to this compressive load, which will be equal to minus N by A, plus due to this movement, clear, and this movement due to this By, it will bend like this. So we are interested to find out at section AA, so the upper layer will be in tension, so the bending stress will be positive, so it will be equal to plus M into Y divided by I. Clear? And due to shear stress V, shear force V, will be having shear force which is equal to V into QA divided by I into T. So first we will concentrate on normal load. For that we need A and I, which are the section properties. So you can see over here, if I take it toward downward, let me copy it and paste it over here. So you can see this is the cross section. So what we will do is that we'll find the area, and this area is equal to, area of this will be equal to, if we take this whole as a rectangular box having dimension 20 by 50, so and then we'll subtract these two portions, so we will get the area of this I beam. Clear? So I will write it. The area will be equal to this width, which is 20 millimeter. So in meter it is 0.02 meter, and the height is 50 millimeters, so 0.05 minus this height. This height is, again you can see, 50 minus 7.5 minus 7.5, which is 35, and 35 is minus 0.035. Clear? Into this width, which is, you can see this is 20, this is 7.5, so that will give you 12.5. So 12.5 will be the distance remaining two portions, so minus 0.0125. Clear? And when you calculate it, you will get the area will be equal to 0.5625 into 10 raised to power minus 3, and unit will be square meter. Now I'll find this I, and you can find this I by using equation. I is equal to, for I beam, you can see that this is, if you take the half of it. Clear? So you can see this is symmetrical above and below. So this will be the neutral axis or centroidal axis, so it will be equal to 1 over 12. B is 0.20 millimeter, which is 0.02, and the total height is 50 millimeter, which is 0.05 whole cube, minus the moment of inertia of these two hollow portion. So minus 1 over 12, breadth, which is the remaining, is 125, so 0.0125 meter, into height is 35 millimeter, which is 0.035 whole cube. So when you calculate it, you will get the moment of inertia comes out to be 0.16367 into 10 raised to power minus 6 meter power 4. Now you have both I and A, so you can just put it in this formula. So what we will get is sigma is equal to minus n, and n is equal to 1876.39 minus, divided by area is 0.5625 into 10 raised to power minus 3, plus moment, which is 87.5 into y. Y is distance from neutral axis till the point A. So this is wide y. And this distance, you can see, this distance is 35. So 35 half is 35 divided by 2, which is equal to 17.5 millimeter. So in meter it is 0.0175 meter. So I will write, multiply by 0.0175 divided by I is, which we have calculated, is 0.16367 into 10 raised to power minus 6. And when you calculate it, it will be equal to 6.020 megapascal. So sigma is equal to 6.020 megapascal. Now we'll find shear stress. So for shear stress, we have V, we need V, so V is 583. So 583.3. And what about QA? So QA is equal to y dash bar into area. So you can see A is this point. So above A, this is the area. This is the area. And this area is 20 by 7.5. So I will write this area A is equal to 20. So 20 is 0.020 meter into thickness is 7.5, which is 0.0075 will be 7.5 millimeter is 0.0075 meter. Clear? And what will be the y dash? So y dash is distance from neutral axis till the mid of this section, this area. Let me zoom it from neutral axis till the mid of this section. And you can calculate this distance is 35 and this is 7.5 divided by 2. So this distance, total distance will be equal to 21 point, sorry, this distance will be equal to 20, this from neutral axis till the mid. This distance will be 21.25 millimeter. Why? Because this distance, this distance was 35. So this distance is 17.5 millimeter, and this half of 7.5 will, when you add it, it will give you 21.25 millimeter. That will be equal to y dash bar. So let me write it here. So y dash is 21.25 millimeter or 0.2125 meter. Now you have both the values. So just put it in above. QA will become equal to y dash, which is 0.0122125. 2125 multiplied by area, which is 0.02 into 0.0075, and you will get this QA will be equal to 3.1875 into 10 raised to the power minus 6 cubic meter. So put the value 3.187 into 10 raised to the power minus 6 divided by I, and I is this one, 0.16367 into 10 raised to the power minus 6. And what about T? So T is this thickness, which you can see that is 7.5. And 7.5 millimeter in meter is 0.0075. So when you calculate it, you will get the shearing stress at point A comes out to be 1.515 megapascal. Now you have both normal stress and shear stress. So if you want to represent on element, so it will let this is the element. Clear? So in x direction, this is will be sigma x, which is equal to 6, this 6.02 megapascal, 6.02 megapascal. In y direction, you do not have any stress, so sigma y will be equal to 0, and shear stress is this one plus 1.15. So it will be, the shear stress will be like this. This is tau A or tau of xy is equal to 1.515 megapascal. So now we will find principal stress. For that, I have to copy all this and we will move toward our second page so that we can have all this. Let me copy it. Okay, and we will paste it over here. Resize it. Okay, now we have this state of stress. So you can see that we do not have sigma y, we have sigma x is equal to 6.020 megapascal. We do not have sigma y is equal to 0, and tau of xy is 1.515 megapascal. And in first part we have been asked to find the principal stresses. So we know that principal stresses, which is sigma 1 comma sigma 2, sigma 1 comma sigma 2, or in combine you can write it like this. So it is equal to sigma x plus sigma y divided by 2 plus minus sigma x minus sigma y divided by 2 whole square plus tau of xy square. Clear? So just put the values in this formula. So sigma 1 comma 2 is equal to 6.020 plus 0 divided by 2 plus minus 6.020 minus 0 divided by 2 whole square, and tau of xy is 1.515 square. So when you solve this for plus value, so see, you will get sigma 1, and sigma 1 will be equal to 6.38 megapascal. And when you solve for negative, so you will get sigma 2 is minus 0.360 megapascal. So these are the principal stresses, and that is the answer of our first part. Now we will move towards second part, and in second part we have to specify orientation. We will find theta, or the angle for the plane over which this principal stresses acts. Clear? So we know that orientation of principal stresses. So we know that we can find it by using this formula. Tangent of 2 theta p is equal to tau of xy divided by sigma x minus sigma y divided by 2. Clear? So put the value. Tau is 1.515 divided by 6.020 minus 0 divided by 2. So you will get tangent of 2 theta p will be equal to 0.5032. And when you solve this for theta p, so you will get this theta p will be equal to 13.36 degree, or this will be theta p1, or theta p2 will be equal to minus 76.64 degree. So we will now specify these principal stresses on the element. So let me show you. This was the original element having normal stress sigma x in this direction. That was sigma x and tau of xy like that. This was tau of xy. Clear? And we have find this plane. So this was the initial x-axis. This was y-axis. Clear? So theta is 13.36, which is positive. So it means that this is counterclockwise. So your new axis or transform axis, this is theta p1 is 13.36, will be this one, and this will be your new y dash axis. And when you draw the element like this, clear? So normal sigma 1 will be now we do not know that whether on this theta p1 what will be the value of stress. So what we will do is that, let me do it as well. Substitute theta 1 is theta p1 is equal to 13.36 in stress transformation equation, which is sigma x dash is equal to sigma x plus sigma y divided by 2 plus sigma x minus sigma y divided by 2 into cos of 2 theta plus tau of xy sine of 2 theta. Clear? So when you put sigma x and sigma y, let me put it as well. Sigma x is 6.020 minus 0 divided by 2 plus 6.020 minus 0, this is plus, this is minus, divided by 2 into cos of 2 theta. So 2 theta is 26.71 degree, plus tau of xy, which is 1.515 into sine of 2 theta, and 2 theta is 26.71 degree. So when you solve this, you will get sigma x dash is equal to 6.38 megapascal. So it means that at an angle of 13.36 over that face, we have sigma 1. So we will represent the element over here. This is plus value. So it will be, this will be the, on this face, it should be perpendicular. So this will be sigma 1. Clear? This will be sigma 1, and sigma 2 is negative. So it will be compressive. This will be sigma 2. Sigma 1 and sigma 2 are principal stresses. Clear? And this is the answer of our third part. These are the answer of specify the location, and the third part was indicate the result on element on the point stress. So this is the answer of our third part. And that was all about this problem 9-31. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 9-32. This problem is taken from chapter number 9, that is stress transformation, and book name is Mechanics of Material by R.C. Hibbler. So statement is determine the maximum in plane shear stress developed at point A on the cross section of the arm at section AA. Specify the orientation of this state of stress and indicate the result on the element at a point. So you can see this is the arm, and that there is a 500 Newton load applied at point B. We have a pin support, and there is a rope CD which support this arm. Clear? And we have to find at the cross section AA, the cross section of the beam is shown over here. So at this cross section, we have to find the maximum in plane shear stress at point A, and then we have to specify the orientation of this state of stress and indicate the result on the element. So let's start with the solution. So first step is that we will determine the support reaction. So if you remove this support at point B, so you will be having a reaction force in horizontal direction, which will be like this. This will be Bx. Clear? And on vertical direction, you will be having a force which will be acting downward, that is By. And this rope acts a force in this direction, which is FCD, and this FCD makes an angle of 30 degree with this arm. Clear? So we will find these support reactions, this Bx and By, and force in rope, which is FCD, by using equation of equilibrium. So first equation of equilibrium is that sum of all moments about point B is equal to 0, and taking the counterclockwise movement as positive. So you can see this is a point B. So these two forces are passing through point B. It is not producing movement, and the only force which producing movement about point B is this 500 Newton and the vertical component of this force. So this force FCD will have two component, rectangular component, one which is in this direction. This will be equal to FCD X component, and the other component is this one, which is equal to FCD Y component, because you can see this will be the Y component. Clear? So this FCD Y will be equal to FCD sine of 30 degree, and this FCD X will be equal to FCD cos of 30 degree. So you can see that this FCDX is passing through point B. It is not producing any movement. So this component, which is FCD sine of 30, will produce movement because the perpendicular distance is this 0.3, and it is producing counterclockwise movement. So it will be positive. The second moment about point B is this 500 and perpendicular distance is this 0.65 and it is negative, but their sum must be equal to 0. So I will write it FCD sine of 30 degree into perpendicular distance is 0.3 minus 500 into perpendicular distance is 0.65 and is equal to 0. So from here you will get this FCD will be equal to 2166.67 Newton. Now you will find this Bx by using equation of equilibrium that sum of all forces along x direction must be equal to 0 and force in this direction is taken as positive. So Bx is in positive direction while FCDx is in negative direction. Their sum must be equal to 0. So I will write Bx minus FCDx which is equal to FCD into cos of 30 degree is equal to 0. So Bx minus FCD is 2166.67 into cos of 30 degree is equal to 0. So when you calculate it, you will get this Bx will be equal to 1876.39 Newton. Now you can find By by using the third equation of equilibrium that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So three forces. One is this By, other one is FCDy component and the third one is 500. Their sum must be equal to 0. So By is downward, so minus By minus 500 is also downward plus FCD sine of 30. So FCD is 2166.67 into sine of 30 degree is equal to 0. So from here you will get this By comes out to be 583.3 Newton. Now these are the reaction forces and we have been asked to find the principal stresses at section AA. So for that we will cut the beam over here and we will find the internal loading at section AA. Clear? In order to get the scenario that what are the force applied at section AA. So at section AA, let me choose another color. So if you section it, so you will be having free body diagram will be like this. This will be like this. This is point B where we have Bx in horizontal direction. So Bx, we have By in downward direction. And distance between this is section AA. AA. The distance between By and section AA is 0.15. So when you section it, you will be having a normal force acting on this face and that will be, let this is down N and opposite to Bx in order to keep in equilibrium and the shear force which will be in upward direction and you will be having a movement as well. So we'll find this N, V and M by using equation of equilibrium that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So By is downward, so minus 583.3 plus V is equal to 0. So it means that this shear force is 583.3 Newton. Now we have this V, we can find Bx. So for Bx we will apply equation of equilibrium that sum of all forces along x direction must be equal to 0 and the force in this direction is taken as positive. So Bx which is in positive direction, so Bx is 1876.39. Clear? Minus n is equal to 0, so it means that n is also equal to 1876.39 and the unit will be Newton. Now we'll find this moment by using equation of equilibrium that sum of all moment along section AA is equal to 0 and taking the counterclockwise moment as positive. So you can see this force By into perpendicular distance is 0.5 is producing moment in counterclockwise, so it will be positive, and this moment which is producing clockwise moment and that is negative, their sum must be equal to 0. So I will write By is actually 583.3 into perpendicular distance is 0.15 minus this moment will be equal to 0. So from here you can see the moment will be equal to 87.5 Newton into meter. Now you have all these unknowns, so you can see here that due to this n compressive stress you will be have a normal stress, normal, clear, and due to this moment, and due to this we'll be having a moment, and this moment will cause the beam to bend like this, clear, and the upper portion will be intense tensile stress, there will be tensile stress. So we will have a combination of normal stress and bending stress. In upper it will be positive and in downward it will be negative. Since this point A is above the neutral axis, so we will take it plus. And due to this shear force, we will be having shear stress. So I will write it shear stress due to V, due to V. So that shear stress will be equal to, at point A, it will be equal to V into QA divided by I into T, and normal stress at A is due to the compressive stress, which is N by A, and that is negative because it is compressive, plus the stress due to movement, which is My divided by I. The positive sign is the reason that due to this movement this will be bend like this, clear. So this A point lies upward, so it will be positive. Okay, so we'll find this shear stress and normal stress. So for normal stress, we need A, which is the cross sectional area, and I. So you can see this is the cross section of the beam, so A will be equal to, if you take it as a rectangle, clear, so this a rectangular area will be 20 by 50, so 20 in millimeter, so in meter it is 0 0.02, and height is 50, so 50 in meter is 0 0.05 meter, so 0 0.05. This is the area of this rectangular cross section, so we will subtract the area of this two shaded portion. So this height, you can see this is 50 minus 7.5 minus 7.5, which is 35, and thickness is 7.5. Clear? So thickness 7.5, so 20 minus 7.5 will be 12.5. So the remaining, this portion is 12.5. So I will subtract it, minus 35 millimeter, which is 0 0.035 meter, into the remaining was 12.5, so 12.5 is 0 0.125 meter. So when you calculate it, you will get the area of I beam, which comes out to be 0 0.5625 into 10 raised to power minus 3, and unit will be square meter. Now we'll find I, which is the moment of inertia, and moment of inertia for this symmetrical I beam, about the half will be, or its neutral axis will passing through centroid, because this is symmetrical, clear. So it will be equal to 1 over 12 B, which is 20. So 20 in meter is 0 0.02, and height is 50 millimeter, which is 0 0.05 cube, 1 over 12 BH cube, minus the moment of inertia of this remaining two portion. So this height was 35 millimeter, which is 0 0.035, and the remaining two portion is this one, clear. So minus 1 over 12, breadth is 0 0.0125, and height is 0 0.035 meter, and it will be cube. So when you solve this, you will get the moment of inertia comes out to be 0 0.16367 into 10 raised to power minus 6 cubic meter. Now you have A and I, so you can put in this formula. N is minus 1876.39 divided by area is 0 0.5625 into 10 raised to power minus 3, plus movement is 87.5 into y. Y is distance from neutral axis till point A. y. This is ya, and this ya is equal to, this total distance is 35, so 35 divided by 2 is 17.5 millimeter. In term of meter, it will be equal to 0.0175 divided by I, and that I is 0.16367 into 10 raised to power minus 6. And when you solve this, you will get the normal stress due to this uh, two stresses will be equal to 6.020 megapascal. Now we will calculate shear stress, and we know that shear stress at point A is V into QA divided by I into T. So what will be Q? What will be V? V is this one, and QA is equal to Y dash bar into A. So A is this area which is above the point A. This is your A, and this A is 7.5 millimeter thickness and width is 20 millimeter. So I will write the value of A 7.5, which is 0.0075 clear, into its width, which is 0.02 meter. And what will be the y? So y dash bar is distance from neutral axis till the mid of this section, and this distance is y dash bar, and that is 21.25 millimeter. Because this distance is 17.5, you can see, and 7.5 divided by 2 will be this distance. When you add it, it will be 21.25. So I will write 21.25 is 0.02125. That will give you QA. And when you solve this, you will get QA will be equal to 3.1875 into 10 raised to power minus 6. So put it in this formula. Shear stress at point A is V. So V is 583.3 into QA is 3.1875 into 10 raised to power minus 6 divided by I. I is 0.16367 into 10 raised to power minus 6, and T. So T at point A is, you can see, this is 7.5 millimeter, which is 0.0075 meter. So when you solve this, you will get the shearing stress at point A comes out to be 1.515 megapascal. Now if you draw it on element, so let this is the element. So normal stress at point A, which is sigma x, is this one in x direction. This is sigma A, or you can also write it sigma x. So this is sigma x, and there is no sigma y because there is no stress in y direction, and shear stress will be like this. This is tau of xy, or that is tau of A. This is tau of xy. Clear? Now this problem is ready to solve. Our first part, determine the in-plane shear stress. So for that, I will copy all this data and we will move toward our second page. Let me copy it first. I'm going to copy it and we will move toward next page. Here I will paste it and resize it so that we can see the. Now focus over here, that you can see on this element. Here we have sigma x is equal to 6.020 megapascal. Clear? Sigma y is not available, so it will be 0, and tau of xy is 1.515 megapascal. In part first, we have been asked to determine the maximum in-plane shear stress. So maximum in-plane shear stress at point A. So we know that maximum in-plane shear stress is equal to sigma x minus sigma y divided by 2 whole square plus tau of xy square under the root. So put the value 6.020 minus 0 divided by 2 whole square plus tau of xy is 1.151 square under the root. And when you solve this, you will get maximum in plane shear stress comes out to be 3.37 megapascal. So this is the answer of our first part. Now we will move towards second part, and in second part we have been asked to specify the location orientation. Specify orientation of this maximum in plane shearing stress. So we know that maximum orientation of in plane maximum shear stress is can be represented by this formula. Tangent of 2 theta s is equal to minus sigma x minus sigma y divided by 2 divided by tau of x y. So put the value minus 6.020 minus 0 divided by 2 divided by tau of x y, which is 1.515. That will give you tangent of 2 theta s. So tangent of 2 theta s will be equal to minus 1.9871, and this theta 2 theta s will be equal to tangent inverse minus 1.9871, and you will get this 2 theta s will be equal to minus 63.29 degree, or theta s will be equal to minus 31.6 degree. And there is another plane which is theta s2. This will be theta s1, and theta s2 will be equal to 58.4 degree. I will show you in a while how we will get this. Now we have theta one plane at angle of minus 31. Minus 31 means this angle is the element rotates 31.6 degree clockwise, and the theta s2 is either it should rotate 58.4 in counterclockwise. So we want to check it. So put theta is equal to minus theta s1 is equal to minus 31.6 in shear stress transformation equation, which is tau of x dash y dash is minus sigma x minus sigma y divided by 2 into sine of 2 theta plus tau of xy cos of 2 theta. So let me put it. Tau of x dash y dash will be equal to minus 6.020 minus 0 divided by 2 into sine of minus 63.29 plus tau of xy, which is 1.15 into cos of minus 63.29 and degree. And when you calculate it, you will get this tau is 3.37 megapascal, which is the same maximum in plane shear stress. But we have confirmed that if you draw the element, let this is the initial axis x and this is y, clear, and when you rotate it through angle of minus 31, so minus means clockwise, so this will be, let this is your new x dash, and this theta is your theta s1 is 31.6 in clockwise direction. So your y new y dash or transform axis y dash will be this one, and if you draw the element like this, so this will be the element, and you can see that tau of x dash y is positive, so it should be in upward direction. This is in y direction, positive y dash direction. So this is tau of x dash y dash, our maximum in plane shear stress, clear. So we have represented on element. So with this we have also average normal stress. So average normal stress, and we will also represent it. Average normal stress is equal to sigma x plus sigma y divided by 2. So 6.020 plus 0 divided by 2 will give you average. So average normal stress comes out to 3.01 megapascal. Pascal. And if you want to represent this is positive, so it means that this should be in positive direction. This is average normal stress. So these are the answer of our second part, and this representation which is indicate it on element. Clear? And this is the answer of our third part. Clear? And you can see that this is the angle 31.6, either to rotate it in clockwise direction, or this is anti-clockwise direction. This is theta 2s, which you can see that if you subtract 90 degree minus 31.6, so it will be equal to 58.4 degree. Clear? So in that direction you can see you will also have a shear stress, and transform shear stress or maximum in plane shear stress. And that was all about this problem 9-32. I hope you have enjoyed this video and you are learning as well. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching.